This is Bhavani. Today my presentation topic is pipelining. Here I'm giving the information about pipelining and I'm giving some examples of pipelining. Before pipelining concept, we need to know about the propagation delay and the frequency. Um, if we understand these concepts, then the pipelining concept will be understand easily. Okay, what is propagation delay? Propagation delay is the amount of time required for a signal to be received after it has been. Means propagation delay simply known the like it takes time starting to ending. Okay, here I'm giving a example. I'm taking some circuit diagram. The circuit diagram is combination of logic gates. I'm giving the each logic gate. I'm giving some time. Here 2 milliseconds, 3 milliseconds, and 3 milliseconds. Here two and one. I'm giving the milliseconds. This is the input and this is the output. Um, Here, we observe one thing. The propagation delay means the longest path. Okay, longest path is known as propagation delay, or it's take uh, highest time. Okay, 2 plus 3, 5 plus 3, total 8 milliseconds, and 2 plus 2 plus 3 is the 7 milliseconds, and 1 plus 2 plus 3 is more total 6 milliseconds. Here the highest time is 2 plus 3 plus 3 is the highest time 8 milliseconds. This path is known as critical path, and this is the total propagation delay is 8 milliseconds. Okay, after that, frequency. The frequency means the rate at which we are getting output frequently. Okay, it is known as frequency. The frequency is equals to 1 by propagation delay time. Here we are taking worst case. Okay, worst case propagation delay time. Example, PD time is equals to 5 milliseconds. Sorry, propagation delay time is equals to 5 milliseconds. Then I apply to the this formula. F is equals to 1 by 5 milliseconds is equals to 0.2 kilohertz. Okay, here one more thing is I want to reduce the propagation delay time. How? How to reduce the propagation delay? Simply, the solution is to increase the size of the transistor width. Okay, then the flow of content is easily. So then it take the time. It take the less time. Okay, to reduce to we need to reduce the PD propagation delay. So to increase the size of the transistor width. Okay, this is the pipelining. Here, uh, here 5 milliseconds. I take 5 milliseconds. This 5 milliseconds is divided into two parts. Here 2.5 and 2.5. Here the this 2.5 milliseconds are connected into one special block. This the P naught is known as the special block. The special block is connected to the clock. Okay, the input and output. This is the uh, circuit diagram of pipelining. Here, here um, this P naught is equals to partial output. Okay, this is not output of this 2.5. This is the partial output. Um, this partial output is isolated by the given new new input. Okay, here some steps are there. In the four steps are there. The four steps we will understood this concept. Okay, here first step is it will open the gate exactly at 2.5 milliseconds. Here the clock is connected to the special device. First point is it will open gate exactly at 2.5 milliseconds, and second point is it will pass the value from left to right. Okay, yeah, first is it opens the 2.5 milliseconds. The gate is the open. This is the gate. After that, it will pass the value from left to right. So here, left, for example, 0 in left side, it passes the value left to right. Here 0 to 0, it passes. Here the value is 1, it passes to the right. Okay, and it stores the value. Third point is there are next after that, after storing the values, uh, close the gate. Okay, this is the process of pipelining. Here, here I'm taking one example. Here I'm giving the input voltage is AI. So after 2.5 milliseconds, it process coming to this side is the A naught, A P naught. Okay, after the 2.5 millisecond is applied to the special device, um, the gate will open exact 2.5 milliseconds. After the store the data, it stores the AP not the value. After that, it close the gate. Okay. After that, it pass the um, 2.5 2.55. After that, the value AP naught is after 2.5 milliseconds. It goes to the this side. Okay, sorry, passes to this side. Then the output is formed. Here the two table, here one table is there. I take 0 at the time seconds. I am giving the input AI. After 2.5 milliseconds, it passed to here. Okay, AP at 2.5 milliseconds, the special block is will open 2.5 milliseconds, and the AP is passed to here, and it is able to produce the output after 2.5 milliseconds. Then the AP is passed to here, and the gate output is A naught. So with the help of pipelining diagram. Okay, here we observe the propagation delay time is 2.5 milliseconds. Okay, um, and the frequency is equals to 1 by propagation delay time. That means worst case propagation delay time. So 1 by 2.5 milliseconds means 0.4 kilohertz. Here latency. Latency means, what is the latency means? Here it did not give any output. Here observe that output here the 2.5, here there is no output is formed. Only one block is only um, one time. Okay, one time is here empty. Okay, this empty where means latency means this is empty. Number of empties is known as latencies. Okay, here one empty is there, so this is the one latency. And another way is also known. Here number of blocks is used. Okay, here only one special number of special blocks in circuit diagram. Okay, this is the latency. Here one, here we used only one special device. That's why latency is 1. Okay, this is a simple funda. Here I am taking another example of pipelining. Here I am also taking a different milliseconds, and before example I am only taking the same times milliseconds. Uh, Here I am taking the different times. Okay, here 4 milliseconds and 6 milliseconds, 5 milliseconds. Okay, here we applied the 4 steps. Here I am taking the input AI. After that, after 4 milliseconds, it's come to the here. So AP1. After that, it will open the exactly 4 milliseconds and it store the data, store the input AP1. After that, it close the gate. For here, I'm taking 4. 4 plus here 6 milliseconds. Here already taken 4. So how many times we need to take? 2. Okay, so here I want to take again 4 milliseconds. After 8 milliseconds, the P1 AP1 is coming to this side. So it is as a AP2. The totally 8 milliseconds. After that, the clock also, after that it will get open uh, exactly here. So we did not said exactly the clock timing. Okay, so uh, mm, here why, because here four different times are there. That's why uh, uh, That's why we take the worst case propagation delay. Okay, in this, which is the worst case propagation delay means it's take highest time. Okay, in this the 6 milliseconds is the highest time. That's why the clock we will take the 6 milliseconds. Okay, so every time we will be take 6 milliseconds, it will be easy to get the output. Okay, here I'm taking a 6 milliseconds. The output will be like that. Here observe that the frequency is equals to 1 by 6 milliseconds, 0.116 kilohertz. Here latency is two blocks are there. Here two empty outputs are there. That's why latency is 2. Another side, here we use the two special blocks are there. That's why the latency is equals to 2. Here, I'm taking one more example. Here I'm taking three special blocks are there. That's why latency is 3. In shortcut, there is no use of this table. So simply we said like that in circuit diagram. Here, I'm here 6 milliseconds and 358 in total. Total time. Which one is the worst case propagation delay time is 8 millisecond is the worst case. Why? Because this is the high time. Okay, 8 milliseconds is the highest. That's why this is the propagation delay time. So the frequency is equals to 1 by 8 milliseconds is equals to 0.1.25 kilohertz. Latency is 3. So we observe on that every 8 milliseconds the output will be found. Okay. Here also every 2.5 milliseconds. Okay. The output is the output is coming from every 2.5 milliseconds. That's why we given the frequency 1 by 8. Here also I'm giving one more example. I'm giving here in circuit diagram, I'm giving different times, and I'm taking up four special devices. That's why I'm taking four special devices, then latency is equals to 4. Here the worst case propagation delay is 9 milliseconds. And so here 1 by 9 milliseconds is equals to 0.11 kilohertz. This is the pipelining. Thank you for watching.